Hello, this is Rourke Peterson, and this is the solutions to exam 1 for me313. And so first we'll look at the first problem here. Part A asked for what the turbine outlet temperature was. That would be T5 right here. And we were given what the inlet temperature was in the problem, and that was 1473. So the way we want to do this is we're told that this efficiency is 80% as well. So the first thing we need to do is recognize that helium is an ideal gas, and so we have a relation that, for example, T5 over T4 is P5 over P4 to the K minus 1 over K. It's assuming a constant heat capacity. And this right over here is just 1 over the pressure ratio, which was given in the problem. And this would be for an isentropics, that would be T5S. And so then we would go ahead and use our efficiency of our turbine equation, which is going to be for a turbine the actual work produced over the isentropic work. So that would be Cp, and the actual then is going to be T4 minus T5 over Cp T4 minus T5S. CP's are going to cancel. And so then we go ahead and just plug in that right there. So we can come over to EES, and what I have here, you'll see at the top, is just a bunch of stuff that was given in the problem. Values of R and CP, values of K, pressure ratio, pressures and temperatures, and mass flow rates. So here are my turbine equations using the pressure ratios and the isentropic relation and then the turbine relation. So if we go ahead and solve that, we can get our outlet temperature of right there at 783.8. Alright, so let's come back over here and we'll look at part B. And part B said what is the power requirement of the compressor, and we were given what the network is of the whole system. And now that we know what the outlet temperature is, in fact we just calculated the actual work right there, so T4 minus T5, so we can find out the turbine work. So the difference between the network and turbine work is going to go ahead and be the compressor work. So W net is the work generated by the turbine minus that by the compressor. So we'll just go ahead and solve that equation for the compressor. So coming back to EES, there's my equation with the turbine work, actually calculating it this time with CP and then finding the difference. And so then we look over and find out what our compressor work is at 731.5. Alright, so now we're coming over here to part C. What's the lowest temperature in the cycle? So if we look at this cycle, and let's go ahead and just draw our TS diagram to remember what this looks like. TS, and we've got a isentropic compressor, and we're going to up there, we have a non-isentropic turbine right there. So we have points 1 to 2. We're going to go ahead and go through a regenerator, so we're going to point 3 somewhere in the middle, 4 up there, 5 here, and 6 somewhere in the middle. So we realize our lowest temperature is 1. So we need T1. We don't have T1. We also don't have T2. So it's 2 unknowns. So what means we need to do is do 2 balances over that. And what we're going to do is we're going to apply both the first law and the second law across this. And this actually, those combined come out with a pretty simple equation. If you remember that the work, this is actually on your equation sheet, is going to be KRT over K minus 1, and then this would be P2 over P1 to the K minus 1 over K minus 1. That's just a combination of the first and second laws over here. We just found the compressor work, so then we can go ahead and find out what T1 is from that equation. So I'll go ahead and enter that. There's my compressor equation using the mass flow rate, KRT1, etc. I'm also going to find T2 over T1 there. It's not actually needed for this part, but we're going to need it in the next one. So if we come over here, we can now find out what T1 is at 250. We also solve for T2, which is 602. Alright, so now coming over to part D. And what we know is what's the combustion chamber inlet temperature. So that's going to be T3. That's going to be this temperature right there. So now we need to take into account this regenerator to figure out where 3 is exactly on that line. So a perfect regenerator, this would be straight across and straight across. So it'd be a perfect one. In reality, we've got something like this dotted line right over here. So T3 is going to be somewhere down there. The constant heat capacity, this difference between this right there is going to be the same as this right here. So I can go ahead and use my efficiency of my regenerator and find out where this would be, because it's going to be 90% of the energy that I can have. So coming back to ES, here is my efficiency, EFF, that's my 90% efficiency of my turbine. And I've got 5 minus 6, and then my T underscore 6, this would be like the ideal temperature, T6, and so it's going to be 90% of the energy. And then if we look back at our figure, we'll realize that T6, again, being the ideal T6, which would be somewhat lower than the actual T6, is going to be the same as T2. So we can go ahead and find out exactly what our T2s are, which is going to be, and our T6s in terms of that equation right there. And if we come back to our diagram here, you can realize where, so I've got 6 as the actual point right there, and then this is the one that I called underscore 6, which would be kind of the ideal one. And all right, so now coming back to the cycle thermal efficiency. If I want to do that, my thermal efficiency is going to be net work over Q in. That's also going to be 1 minus Q out over Q in. So you can do it either way. Oops. You can do that either way. So if we come back to ES, we've already got the network, so we can do it. Just kind of look at all of them and make sure that the energy balance closes. I went ahead and found both Q out and Q in to get my thermal efficiency, and your thermal efficiency, A to TH, is 47.63. So that's the last part to that problem. Okay, so now let's go ahead and look at problem 2. This is of the Rankine cycle. And the first part of the problem asks what the specific enthalpy is, H7, leaking a high pressure turbine. So that's this point right over here. So we're midway through. So in this problem, we're also given the efficiency of a turbine. And this is going to be done similar to like we did in the last problem, where we've got the actual work over the isentropic work, but now we don't have an ideal gas. So this will just simply be H6 minus H7 over H6 minus H7S. But now to go ahead and find H7S, the isentropic relation is essentially, we'll know we're at P7, but our entropy is going to be the entropy at S6. So I'm going to go and use EES to solve that for me. So here I have all of my given parameters up at the top, my isobaric steps, but here's the turbine. So I'm just having EES look them up at 6. And then my H7, you can see I'm using the entropy at 6 and then the efficiency of my turbine. So if I go ahead and do that, I can go ahead and find out what H7 should be. It should be 1200. The ideal would have been 1178. So coming back over here, so now part B, we want the specific work requirement of the pump. And so this is going to be down here at pump 1. We could do a similar thing like we just did up there with an efficiency of 100%. And so we know what the enthalpy is at point 1. This is a saturated liquid. So we know H1 is going to be at P1 and at X equals 0. You also might remember that since we're pumping liquids, that the actual work for the pump work right over here is going to be essentially V, and then this is going to be the difference in pressure. So P2 minus P1, and this would just be V of a saturated liquid going in. V1 and V2 are essentially the same. So either one of those two things will give you the same solution. And so then here I've got it, and the condenser, there's my value of the enthalpy. In here I'm using volume times P2 minus P1. I need to convert into BTUs, which is what that one is, and you realize your difference in enthalpy is about 3, so it's going to be 3 BTUs per pound mass, and it asks for it in a per pound mass unit. Okay, so coming over to C, now we're at part C. And it says we want to go ahead and find out the mass extracted. So let's go ahead and call that fraction y. And so it means we're going to have 1 minus y coming down at this point over here. It says to use an energy balance over, kind of a hint here, over this whole system. So if I look at the energy balance over that right there, H5 is what's coming out. What's coming in is y times H7, and then 1 minus y times H2, right, coming in there. So and so we can go ahead and we just found out what H2 was, because from our part B, we know what H7 is. We got that from part A. And so the last thing we need to know is what H5 is. And we were told that this is a saturated liquid, so we're at P5 and at X equals 0. So we can go ahead and find out what H5 is. So we can go ahead and solve this equation right over here to find out what Y is. So here's my equation. I just go ahead and have EES look up my value of enthalpy. It's that of a saturated liquid at H5, and then my energy balance for y, and y is about 38%. All right, so let's go ahead and go down to our next part. This is part D. We want to know what the thermal efficiency is of the whole system. And so what I can do here is to find my efficiency, I can either calculate the total work, which would be the second part of the turbine, or I could also recognize that the thermal efficiency is 1 minus Q out over Q in, because I actually already have those values, because Q out is going to be 1 minus Y, and that's going to be H8 minus H1, and then I can go ahead and Q in. We already know what H5 is, or sorry, H6 minus H5. So we can go ahead and do it that way, and that's I think the way that I chose to do it. So here we went, and I found the second stage of the turbine, which was H8S, and then using again the efficiency of the turbine, and then Q out and Q in to get the efficiency of my cycle. And the efficiency of the cycle is 29.6%. And the last part, part E, just said if this was a simple Rankine cycle, so let's kind of imagine what the simple Rankine cycle is. It goes there, we had a perfect pump, not a perfect turbine, went down this direction. And so you had to kind of calculate, this point right over here is still going to be the same. This point right over here is going to be more or less the same. This point right over here is more or less the same. So you just need to go ahead and get rid of your mass fractions in there. And you can go ahead and probably pump that out pretty quick. And you find that the efficiency of that is about 26.2%. So, and that would be part E.